Okay, hello everyone. We are going to start a new topic today called heat and thermodynamics. And we're just going to limit it to 3 lessons. The first one's on expansion contraction, which is what we're going to look at today in this video. And then next we'll do the rate of heat transfer, and then we'll look at the laws of thermodynamics. But before we get into today's notes, I want to show you how this grand topic fits in with the scheme of things that we have been talking about. So I don't know if you remember this, but back at the beginning of the school year, I told you that the topics of physics were broken down into 5 main categories. The first one being mechanics, the study of motion, and I tried to stress that we were going to spend an extraordinary amount of time in mechanics and not spend an equal amount of time in each of the respective areas. But I want to look at the study of mechanics for a minute, the study of motion. So I want you to think back to Galileo a long, long time ago. You know, Galileo and Copernicus, claim to fame, is studying the motion of the heavens and the earth and the planets, and I'm going to call it big things, like big things that they could see. And then we kind of worked our way down to cars traveling down the street, airplanes, boxes traveling down an inclined plane, but all objects that were very, very visible and things easy to picture. And then we moved into fluids. You could also think of a fluid as a whole bunch of molecules where each individual water molecule, did its thing, moving through a pipe or moving through the river. So smaller pieces, but they still had motion with fluid dynamics. And now as we go into heat and thermodynamics, we're definitely looking at things from the molecular standpoint, the size of a molecule, or maybe even the size of an atom. But things are getting smaller. The next topic that we're going to be looking at, starting, I'll say next week, is going to be electricity, circuits, magnetism, and these are charged particles. So now we're going to go deeper inside the atom, and we're going to maybe pick out the electron that has a negative charge, or we'll pick up the neutron that has a neutral charge. And then we get into waves. We get even more, I'll say, invisible fields that are happening around these charged particles. And then when we end the school year, we're going to be looking at nuclear physics and atomic physics, which is actually looking just at the nucleus then of the atom, and then looking deeper inside the nucleus to maybe subatomic particles like quarks and muons. And so I find it interesting 2 things. Number 1, that the topics that we study in physics are arranged from big to small. And what I like even more than that is that our story is a historical perspective. So, back in the 1600s, we only studied the things that we could physically see. We weren't studying subatomic particles because we didn't see them. We didn't have the technology to know that they even existed. And now, all of the research in physics that's going on is at the subatomic level because we're having greater technology advances. And so our story is not only from big to small, but we're actually talking about things like in the order that they were discovered. Like as we talk about heat and thermodynamics, we hadn't discovered the electron yet. So far we think that everything in life is positive. And so I want you to keep that in mind as we go through the subsequent units that are coming up, that this is also a historical perspective of what happened. All right, today's lesson is pretty simple, and it is based on what's called thermal expansion and contraction. So as you know, common sense, when temperature increases, a substance expands, and when temperature decreases, a substance contracts. And so as we talk about 2 examples here, I ask you to consider a balloon, that there's air, gas inside the balloon. And let's make our second example like a spoon. Okay, so you're going to put a balloon in the freezer, and you're going to put a spoon in the freezer. So it says, which substance expands or contracts the most? So, expand contracts the most. Which substances are going to change the most? I think when I put my balloon and my spoon in the freezer, I expect my balloon to contract more than the spoon is going to contract. And then we'll talk about expanding. Maybe I'm going to take my spoon and my balloon, and I'm going to fire the blow dryer at them for a couple of minutes and kind of heat them up, I'm going to get the balloon to expand a lot easier than the spoon. So in general, what I want you to just know is that gases expand and contract the most, and solids expand and contract the least, and liquids are going to fall someplace in the middle of that story. All right, but that actually makes an interesting next thing to talk about. So even though we have solids, liquids, and gases, I want you to know that water is an exception to the rules of expansion and contraction. I'm not saying all liquids are an exception. I'm saying water is an exception. So if you think back to what you learned in biology, all of the special things and special properties of water, that's going to come into play here in physics also. So it says, at what temperature does water ice have the least volume? So let's pretend it is 70 degrees Fahrenheit outside, okay? And so we have a glass of water. And then as nightfall comes, the temperature goes from 70 degrees Fahrenheit down to 60 degrees Fahrenheit, down to 50 degrees Fahrenheit. And just like you would expect, because it's cooling off, the liquid, liquid water, is going to contract, just like you would expect. Just like you'd expect, all the way down to a temperature of 39.2 degrees Fahrenheit. So like water behaves just like you would expect down to 39.2 degrees Fahrenheit. And then it starts to do something weird. Then as I drop below 39.2 Fahrenheit, it actually starts to expand. And at some point in here, like when it gets 32 degrees and it turns to ice, you know that water expands when it's ice, because when I put my water in my ice cube trays in my freezer, and then when I take the ice out, the water has expanded in those little cube things. So, but we want to know, or I want you to know, that magic temperature is 39.2 Fahrenheit, which happens to equal 4 degrees Celsius. So those two temperatures are the same. So that's when water has its minimum volume is 39.2. So I want you to think of density is mass over volume. And if at 39.2 the volume is the smallest, so like this is a small number, that would mean that at that temperature, 39.2, the density would be the biggest. And so here at 4 degrees Celsius, the density is the biggest. So at 39.2 Fahrenheit. So again, at what temperature does water ice have the least volume and the greatest density? Least volume, which turns out to be the greatest temperature, is 39.2 Fahrenheit. Or 4 degrees Celsius. All right, when water ice expands when it drops below this temperature, okay, that's the anomaly that we're talking about. Okay, something is cooling and it's not contracting, water's going to expand. And then it says, from an environmental standpoint, what happens to lakes and ponds at this temperature? So I want you to picture like a lake. All right, here's a lake. We'll do this. Here's the mud at the bottom. And it is, it's winter time, and there's a layer of ice, let's say, on top. And so the water down here, it may or may not be frozen down here at the total bottom. But when the temperature, I'll say, warms up, because we're going to pretend it's cold and it's winter. So when the temperature warms up and it gets up to 39.2 now, when it gets up to 39.2 Fahrenheit, this is when the water has the greatest density. And then what happens is this ice starts to melt. But this heavy water, now this heavy water has a big density, and so it starts to sink. And when it sinks, it kind of like stirs up the lake. and it ends up making something that in biology is called the spring overturn. And by stirring up the lake, then you're taking the oxygen from the top layer and you're stirring up all of the nutrients in the lake. And that's why we have a lot of biological growth in our lakes and in our ponds in the spring. So when you look out at a pond and you see it all of a sudden overnight, it turned green and mucky and algae is growing all over the place, you know that spring overturn has just happened in that sense. Okay, so this page, we are now going to turn our idea of expansion and contraction into a mathematical relationship, into an equation. All right, so the coefficient of linear expansion is what goes in this blank. The coefficient of linear expansion or contraction is a mathematical measure of how much a substance expands or contracts. So if you look at the table on the bottom of this page, the coefficients of linear expansion, by the way, that variable is alpha, the Greek letter A, you can see that things that are aluminum are going to expand and contract the most because that has the biggest coefficient of linear expansion. You can see down here that quartz expands and contracts the least in our chart. Let's look at these two things. So let's say I'm cooking and I take a glass pan or a glass dish and I put it in my oven. And so if it's going to get hot in my oven, that's going to tell me that my ordinary glass dish is going to expand, and it actually could crack by putting it in my oven. But that's why we have Pyrex glasses. So somebody has invented a special kind of glass that it expands and contracts less than ordinary glass. And so if I'm actually putting a glass dish in my oven, you're supposed to use a Pyrex dish because it's less apt to expand and contract, or it's going to expand and contract much less, and it's less apt to break when you put it in the oven. So those are some interesting things to kind of think about, how that relates to everyday life. All right, so let's look at our equation here. This is our equation for linear expansion and contraction. So I'm going to make up an example as I explain to you what each of these variables stand for. All right, I want you to picture a big, I'll call it steel beam. And this big steel beam, I'm going to start to draw another steel beam that's going to like not fit on my paper. So this steel beam is part of a bridge. All right, and so L naught, that's how you say it, L naught or L0. L0 is the original length of the beam. So I'll write down original length. And let's just pretend the original length of one of these beams is 20 meters. All right, then the next question that you want to know is, what is the beam made out of? Because we need to know the alpha value, the coefficient of linear expansion contraction. Well, I'm going to pretend that it is made out of steel. Because if I was building a bridge, it's probably out of steel. So you can see that steel is 12 times 10 to the negative 6. So the alpha value is going to be 12 times 10 to the negative 6. All right, and then this stands for delta T. Delta T is the change, that's the delta, the change in temperature, change in temp. Technically, the change in temp is supposed to be in Kelvin in physics. All temperatures are supposed to be in Kelvin in physics. But if I was taking Celsius temperatures, I'd add 273 to turn it into Kelvin. And then if I had another Celsius temperature, I'd have to add 273 to turn it into Kelvin. And so the change in Kelvin is going to be equal to the change in Celsius. So what that means is I can just leave it in Celsius and make it easy on myself. All right, so let's talk about this piece of steel. So this piece of steel is in a bridge, and let's pretend it's a summer day, hot summer day in July. So let's call that, I'll write over here, let's call that 100 degrees Fahrenheit. It's hot in July. All right, 100 degrees Fahrenheit, I'm going to have to go into my calculator conversion menu, and I'm going to have to convert that into Celsius. And that happens to be 37.78 degrees Celsius. And then that steel beam is also in the bridge in winter. And let's just say winter might be 0 degrees. And I guess it even gets colder than that in the winter. But 0 degrees Fahrenheit turns out to be negative 17.78 degrees Celsius. So the change in temperature is going from 37.78 all the way down to negative 17.78. So the change is going to be 37 down to 0 and then down to the negative. So I'm going to have to add those numbers to get the change in temperature. So the change in temperature is going to turn out to be 55.56 degrees. So we have the alpha value, the original length, the change in temperature, and then delta L is the change in length. So if it gets bigger, if it expands, that's how much it's going to expand by. And if you think it's going to contract, then this is how much it would contract by. So if I multiply all these numbers together, which I did, I get 0.013. And the unit is meters. So it's not a very big number. Let me turn that into centimeters by moving my decimal point over. 1.3 centimeters. From a hot July day to maybe a cold winter day. So you might not think that's a big deal. But this beam then on my bridge, half of 1.3 would be what, 0.65. So it's going to expand a little bit this way, and it's going to expand a little bit this way. But the next beam is also going to expand a little bit this way and expand a little bit this way. And basically, because of this expansion and contraction, my bridge is going to break. It's going to crack. And so that's why in real life we have these like expansion contraction joints at the end of the beams so that they can expand and contract by that centimeter or two that they need to so that my bridge stays in shape. So basically you're going to use this equation a lot, the expansion and contraction. Sometimes though you could be talking about like a window. So it's going to expand and contract in the width direction, and it's going to expand and contract in the length direction. So we could call this area expansion and contraction. So instead of having an alpha value, you just have 2 times that alpha value because it's expanding and contracting in 2 different ways. Then you could also have like something that is, I'll call it a cube. We'll call this volumetric expansion and contraction. And so I would like to say that if you're talking about the volume, that it would be 3 times the alpha value, expanding and contraction in the length and the width and the height. But for some reason, once you get to this 3-dimensional model, it doesn't always work that way. So we don't have a 3 alpha. Instead, we replace 3 alpha with another variable, the Greek letter B, which is pronounced beta. So it's really like a bee with a tail on it. And so this is the coefficient of volumetric expansion. Once you get, so coefficient of linear is alpha and volumetric is beta. So if you are doing something with volume, we're going to use the beta column here. And you'll notice that the beta column in many times is 3 times the alpha. Like 9 times 3 is 27. That one works. 3 times 3 is 9. That one works. 12 times 3 is 36. Oh, it's only 35 in this case. So it doesn't always work. It's kind of like a fudge factor. All right, so as you complete your homework, you're going to be using these equations for linear, area, and volumetric, 1-dimensional, 2-dimensional, 3-dimensional. You're going to need these values in the chart, And if it is a liquid, we are going to pour liquids in objects, and those are going to be volumetric, and those are your values down there. Okay, I think you'll find it pretty simple, and if you have questions, please post them on the discussion board.